So this is question 3 from the 2013 MAT. So let k be between 0 and 2. Below is sketched a graph of y equals f subscript k of x, where that function is this. So we've got this cubic as drawn in the graph. A is the area of the shaded region. Right, so what is this function then? All right, so we fixed two of the roots. We've got x is 0, we've got x is 2, and then k is wandering between 0 and 2. So this k point is moving side to side. Without evaluating them, write down an expression for a in terms of two integrals. Right, well, clearly we're going to be splitting it at k. Right, so this is fine. A of k then is going to be the integral from 0 to k of f subscript k of x dx. And then we want to add on this region, and this region is going to be negative, so we're going to want to take off the next integral from k to 2 of f of k of x dx. Nice. Right. Part 2. Explain why a function of k is a polynomial in k a degree 4 or less. You are not required to calculate a of k explicitly. So why is this? Isn't that obviously going to be 4 or less because we're integrating a cubic? Can't be as simple as that, can it? No, it's not as simple as that because we've got k's here and we're going to integrate the x's and turn them into k's. So we could have more k's when we got that one. So you're not required to calculate a of k explicitly. So, but isn't that the easiest way to do it? I don't know, let's go start on that path and then abort going the whole way, maybe. So fk of x is going to be x times, I'm just going to do an x squared minus kx minus 2x plus 2k. So expanded that out. Let's just expand it out fully then. So x cubed, then we've got a minus k plus 2x squared, and then a plus 2kx. I mean, this is just working towards doing the integral. But they want us to not do the integral. It's not even a hard integral to do. Then, okay, so let's just turn into words then. So we're going to get we're going to integrate will give, I mean, why not just do it? I mean, it doesn't say you can't do it. It just says you're not required to, but it's just so easy to do now. Anyway, integration, rather than integrate, integration will give an x to the 4 term and a x cubed times k term and lower order terms. Therefore, when x is replaced by k, the highest order of k will be 4. Highest order will be k to the 4, because we're going to get a k to the 4 from there and a k to the 4 from there. And they might cancel out, so you might end up getting lower order, but we can't get any higher. So that's just a couple of sentences to abort actually doing the integral that isn't that hard to do. Okay, whatever. Part 3. I mean, maybe you could think of a different way of doing that second part, but I suppose that wasn't too long. Verify that fk1 plus t is minus f2 minus k1 minus t. Right, this is just going to be plugging in then, isn't it? So, which also isn't going to be exactly riveting stuff, but fk1 plus t. So that is going to be equal to, we've got a 1 plus t, then we've got a 1 plus t minus k, and then we've got a 1 plus t minus 2, so a t minus 1. So that's that one. And then we've got what is it? F of, minus f of 2 minus k, 1 minus t. So it's all going on. So we've got a minus. Then we're going to have a 1 minus t. Well, at least that's got us the last bracket. Then we've got a 1 minus t minus k, and in this case k is 2 minus k, so minus 2 plus k, and then x minus 2, so 1 minus t minus 2, so minus 1 minus t. Right, so well, we want extra negatives then. Let's deal with, well, I'll make the first bracket the same as the last one, so let's make that a t minus 1 by taking that minus sign in. Then we've got minus 1 minus t plus k. Oh, right, we've got a negative of the middle bracket, and then we've got that. So we can just flip negatives on the last two brackets, and then we get the same thing. We get a t minus 1, a 1 plus t minus k, and then a 1 plus t. So we've got the same setup on both. Okay, so yeah, that was just a bit tedious, and it's filled up the sheet, so let's get a new one. Part 4 then, how can the graph y equals fk of x be transformed onto the graph y equals f2 minus k of x? Right, okay, so clearly that's what they've set us up for with this. So we've got fk 1 plus t is equal to minus f2 minus k 1 minus t. So we want to get this in terms of x then. So that means fk of x means that x is going to be 1 plus t. So this is going to be minus f2 minus k. So if x is 1 plus t, let's just get it, x equals 1 plus t. So t is x minus 1. So that's what we're just putting in here then. So we're getting 1 minus x minus minus 1. So we're getting 2 minus x. Okay. So that's now translating, at least we're starting from fk of x, and we want to get it onto this graph then. So that means that we've got 3 translations here. Well, there's lots of different ways you can do transformations though, isn't it? This is possibly, I wonder if I try and get clever, this might have something to do with a rotation, but let's go simple. Let's say we're moving to the left 2. So we go to the left 2. We then reflect in the y-axis, and then we reflect in the x-axis, which may end up being a rotation. So what's actually happening then with this? So we've started off with this thing here. So we've gone like that. So that's our starting point. We move it left 2, which means we've got exactly the same thing, but now the y-axis is going through there. Then we reflect it in the y-axis. Okay, so that now takes us to what we had is doing that. Okay, but now we've got the big bit on this side. So it's moved k further away, k's moved along. And then we're reflecting in the x-axis. So yeah, we've now got the big bit. So it's looking a similar shape, but now we've got the bigger bit there and the smaller bit there. So it's gone like that. And that has transformed from one to the other. Okay, so that's going to be a rotation about 1, 0 is another way of putting that. I think that's coming out the same way, but still I've got that set up there, or rotation of 180 degrees about the point not 0, 1, 1, 0. Okay, deduce that a of k is equal, so deduce that the area hasn't changed. Well, whatever we do on whichever set of transformations we use, the area hasn't changed. So yeah, if we're just doing a rotation, then nothing's changing. there's no stretches. So you can either talk through, as I have done, I suppose, with these steps of transformation, these 3 transformations, showing that nothing has changed, or just say, well, we've got a rotation if you've spotted that one, and that also means that the area hasn't changed. So yeah, we can put something in there saying, you know, a rotation means area unaffected. Or you could, as I say, go through these steps of saying, well, we've just shifted it. This has got no stretches in it at all. No stretches. And we're back, crucially. You can't just say there's no stretches because we could have moved it out of that region. So we could say, well, we've moved it out, but then we've moved it back again. So we've moved it 2 off to the left and then reflected it back in again. So these 2 steps here, these first 2, left to the 2 and reflecting the y-axis, bring us our area back into that initial 0 to 2 range. So yeah, 2 different ways, but the rotation certainly helps in order to show that the area hasn't changed. Okay, what we got now then? Explain why there are constants a, b, c such that the area is those things. Right, so when we do the integral, we're not going to get any x cubed, well, k cubed, it would end up being, or k terms. So why would that end up being the case? Again, why haven't we just done the linked integral? And it is, you know, it's not really that hard to do. Anyway, explain why there are no constants a, b. I mean, maybe it doesn't come out from just doing the integral, I don't know. Anyway, let's have a look at these. We know we're getting nothing higher than k to the power 4. It's got this k minus 1 in there. So there's probably some way of seeing the matrix on this and realizing that this has got something to do with this rotation point. But I don't know what that's going to be. But we do have this condition in the previous part of the question. So we know that if we put in k and 2 minus k, then they're going to be equal to each other. So we can say that that is going to be equal to a of 2 minus k, which is equal to a, so 2 minus k, so that would be 1 minus k to the 4. And then we'd have plus b 1 minus k squared plus c. So we need to show that those things are going to fit. Explain why there are constants such as that. I mean, that's all right, isn't it? Because the c's would just cancel. And these things are the same as each other because we're squaring. Yeah, I mean, the 1 minus k to the power 4 is the same as k minus 1 to the power 4. Yeah. So you could make that comment then. 1 minus k to the power 4 is equal to k minus 1 to the power 4. And 1 minus k squared is equal to k minus 1 squared. So these things are the same as each other. And, well, you're not going to get that for the odd powers. Because if you had a cubed, if you had a 1 minus k cubed in there, that minus 1 isn't going to go away. So, yeah, is that all they want? Just to put those numbers in? I mean, that 2 minus k and say these things are the same. I mean, that seems to be it. So this has followed a pattern that we've seen in quite a few of the math questions where it's not obvious what the big picture of the question is going to be from the outset. Yeah, we kind of get used to that when we're doing A-level questions. You say, oh yeah, I've seen this before. I know where it's going. I know what the story is going to be. In these math questions, these are unfamiliar situations and there is a story and they walk you through it. And we've got the 5 parts of this question that are walking us through a story, that we've got this particular function. We want to know something about the area. We divide the calculation of the area into these two integrals, then we say something about the area being a polynomial degree 4 or less. Then we say something about how that function can be transformed without changing the area, and then using that to say something about that polynomial degree 4 or less. So it's a path here, but it's an unfamiliar path. And one of the things with doing the MAT is getting more comfortable with walking those unfamiliar paths. I'm saying more about it in this video because I felt the same at the end of this one as I did on question 2 from the same paper. Question 2 and question 3 I think have been more difficult than on previous papers. And sometimes when you're wandering an unfamiliar path, you can be left with less of a warm feeling inside when you get to the end of the question. You know, I'm fairly happy with the answers that I've given here. Okay, I might have made a mistake somewhere, but I'm fairly happy with what I've done. So, you know, that is the end result of this question. I don't feel as though I've made any particular insights into the story of the question, but nonetheless, I've gone through following their instructions and got the answers out. And that can often be the way with MAT questions. I mean, sometimes you get, you know, a flash of, oh, this is what they're after. I can see where it's going. Here's a bit of a shortcut. I can really see what they're getting at. But this one, yeah, I didn't really see that so much. I mean, maybe a little bit with that rotation, which I didn't spot immediately. But, you know, slim pickings on this particular question. But, you know, that doesn't mean to say you've necessarily done it wrong. You know, sometimes in maths, you're just grappling with what's in front of you and seeing where it leads. And for me, that was the case with this question. So we'll see how the rest of the paper pans out anyway in the next, what we got, another 4 questions to do.